Okay, so we're going to have a look at carbon-13 NMR. NMR stands for nuclear magnetic resonance. So it's a spectroscopic technique, the process of which we really don't need to go into, other than to say that at the end of it, when we have a sample, we're going to get a spectrum produced. This is actually the spectrum for the compound 1-bromo-2-chloro-ethane. And the carbon-13 NMR tells us two things really. It tells us how many different carbon environments there are. And if we have a look at this molecule here, we can see that here's carbon environment number 1 and here is carbon environment number 2. What we mean by that is this carbon is bonded to different atoms than this carbon is. So this carbon is bonded to a chlorine and this carbon is bonded to a bromine. What we can also talk about is how many carbons are in that environment, and also talk about the effect of the atoms around them. But we'll come to that come to that in a minute. So if we have a look at a scale on our NMR spectrum, the bottom of the scale is called chemical shift. It's measured in parts per million, ppm, and often has the symbol delta. What's not on this spectrum here is the standard against which we measure all spectra. So, and the standard is something called TMS, which is tetramethyl-silane. TMS is chosen because it's a very stable compound. The formula of it is this. You'll see in a moment it's also chosen because of the silicon atom significantly shields the carbon and the hydrogens, which we'll talk about now. So, probably one of the most important things on a carbon-13 NMR spectrum is the fact that the carbon atoms have peaks at different chemical shifts. Now, the reason that occurs is because of what's called de-shielding, or shielding or de-shielding. The further to the left or further downfield a peak is, we say the de-shielding increases, or it is more de-shielded. So if we have a look at our environments 1 and 2 here, environment number 1 is attached to a chlorine atom. So a covalent bond to a chlorine atom. We know that the chlorine atom is very electronegative. As a result of the chlorine atom being electronegative, it's going to pull electron density off of carbon atom number 1, and therefore it's going to de-shield it, which means it's going to experience the effect of the external magnetic field in the NMR spectrum more. So we don't really need to go into any more detail about the physical process of what's happening, other than to say the further down we find a peak on here, the more de-shielded it is, which means it's having more electron density withdrawn from it. If we compare these two, carbon atom number 1 and carbon atom number 2, chlorine is more electronegative than bromine. So as I said, the chlorine is more electronegative than the bromine there. Therefore, this peak must be due to carbon atom number 1, and this peak is due to carbon atom number 2. Now, carbon atom number 2 has been de-shielded to some extent because bromine is electronegative and is pulling electron density off of it, but it's closer to 0. So just to summarise, the scale, chemical shift, ppm, which we often give the symbol delta to. We measure all spectra against a standard, which is TMS, tetramethyl-silane. There is the structure there. The further to the left or downfield we see a peak, the more de-shielded it is, which it means it's likely to be more likely to be attached to a very electronegative atom or an electron withdrawing group or something like that. It's much easier if we just now have a look at a few examples. So, example number 1 is ethanol. There are 2 different carbon environments in here. That carbon is attached to an oxygen, a carbon and 2 hydrogens. This carbon is attached to a carbon and 3 hydrogens, so it's a different environment. Carbon environment number 1 is going to be more de-shielded because of the electron withdrawing impact of that oxygen atom, that electronegative oxygen atom there. So we expect that to be environment number 1. Environment number 2, there is still some electron withdrawing going on through the molecule, which means obviously the peak for number 2 is not at 0. It has been de-shielded to some extent, but not as much as number 1, which is directly covalently bonded to that oxygen atom there. Notice we've got the TMS standard in this example. Let's have a look at example number 2. So we've got 4 different carbon environments, 1, 2, 3 and 4. We know that because each one of those is attached to something different, and so therefore they are completely different environments. Environment number 2 is going to be hugely de-shielded. So we would expect this one to be the really downfield one, well away from 0. I'm just going to put TMS there as the standard because that oxygen is withdrawing lots and lots of electron density from this, therefore it's de-shielded, it's going to experience the effect of the magnetic field more. If environment number 3 is probably the next most de-shielded because it is directly covalently bonded to an oxygen atom, so that's likely to be this one here, which has been de-shielded. Nowhere near as much as environment 2, but certainly to some extent. Environment number 4 is probably the most stable environment, the most shielded environment, because it's the furthest away from any electron withdrawing groups, so that's likely to be the one closest to 0 there. And then that leaves environment number 1, which is adjacent to some electron withdrawing of this group here, although there will be some interaction between those, which means that this isn't losing too much electron density and therefore hasn't been de-shielded much. So just as a summary, remember that the further we get away from here, the more de-shielded an atom is, and number 2 there is the most de-shielded because it's attached to an oxygen atom. What now remains is for us just to have a look at making sure that we can predict the number of different environments in a carbon-13 spectrum. So we have to think about the symmetry that's taking place in these molecules. If we were to draw a line down here, hopefully you can realise that there is some symmetry there. And also, bearing in mind what we said last time, that if we have a look at this carbon is attached to a hydrogen, so 3 hydrogens and a carbon atom, as is this one. So these are likely to be the same environment, and also as a result of the fact that we have got a plane of symmetry there, so they are effectively the same and same environment. So we would say this would be carbon environment number 2, which then means that obviously these will be carbon environment number 2. We've then got this atom here, which is carbon environment number 3, and then this, which is environment number 4. So we would expect to see 4 peaks in our carbon-13 NMR spectrum. Let's have a look at predicting the number of peaks in the carbon-13 NMR spectrum of 1,4-dimethylbenzene. So again, it'll be well, we have to draw this out. So that's the structure of 1,4-dimethylbenzene, benzene ring, and 2 methyl groups, dimethyl, in positions 1 and 4. Now there's a lot of symmetry in this molecule, and in fact if we are to think about it, there's a line of symmetry here, and there is also a line of symmetry here. So in fact there's not that many carbon environments here. These carbon environments here would be the same because of that line of symmetry, so number 1 there. This carbon environment here would be environment number 2. And then if we look at these, because we have a line of symmetry here, we would find in fact that this is all the same carbon environment. So we have got 3 peaks because we have got 3 different carbon environments. If we have a look at this molecule down here, now because this is a sulfur atom and because of this double bond, there is in fact no line of symmetry I can find in this molecule. So we just really need to count the number of carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8. So in this molecule we would expect to see 8 peaks in the carbon 13 NMR spectrum. Thank you very much.